Good day, everyone. This is Jamal, and today we'll be taking off from where we left off with regards to the 3 by 3 magic square of squares problem. And so, yeah, in our previous video, we were able to work around the magic square of squares in such a way that we had 8 out of 9 integer, 8 out of 9 integers out of 9 possible integers in each of the grids that constitute a 3 by 3 magic square of squares with 6 good sums and out of 8 possible sums. And so, yeah, if you have seen the video, you might have some idea of what I'm talking about. And so today, I'm sharing my progress on this problem, how we were able to further, push the boundaries of this problem, and we've now been able to get all 8 sums right, you know, with still some caveats. So we'll address that in this video, and then, yeah, let's get starting. So share screen. Yeah. And so this was where we ended. We ended. This is just a sketch of what we achieved the previous time. So the only sides which weren't integer in our previous attempt were this side and that side. They give sums contrary to what we had to the 6 other good sums. And so, um, as a follow-up to my previous results, as I've written over here, we will explore with paper, that's on paper, a general approach to the 3 by 3 magic square of squares and close the gaps in the previous part. That's equation 7, so to speak, which was this particular equation. And so on page 4, you know, we had this equation, a squared minus I squared equals this. And then from equation 7, we had this particular equation, which we worked out. And so we had this equation, we had that and that. And what is worth noting is something. I'm going to try to explain this in a way that does not confuse viewers or, yeah, that if you were to strictly, when you go back to this previous equation we saw, if you were to, consider the fact that, because this works, you're only going to strictly focus on this one without focusing on this, there'll still be a gap somewhere. Yeah, and so that was a bit of an email. So sorry for that. And so, well, I take off that. Yeah, this equation serves as the glue between this equation and that equation. And so, yeah, so if you notice what we are doing here, you know, this these two simultaneous equations, that is here, when you come over here, oh, let me go to page 4. Yeah, so when you consider, if we are going to strictly only consider this equation, and and this equation, that's considering this in the previous equation I just showed you, without considering this gap. If you don't consider this equation, because this particular equation, equation 8, serves as the bridge between this and that. And so if you're going to only consider this particular part and consider what I showed you at on page 4, what you'd end up achieving is you'd end up getting indeed solutions that will satisfy this only and satisfy the previous equation as we saw on page 4, but you would have a situation where, by extension, if you work things far enough, you find out that the formula you will get for e squared, or the value you get for e squared in this case, will be different from the value you get from e squared in this case. So this particular equation serves as a bridge in a sense that if you were to flip things a bit, you'd find out that this particular equation is no different from getting c squared plus g squared equals to h squared plus bh sorry, plus b squared. Yeah. And so what's happening is you are solving things by proxy. So when you flip things a bit with equation 7, you have a squared plus I squared equals c squared plus g squared. And when you come here and do a bit of operations here, you find out that that same c squared plus g squared is also equals to h squared plus b squared, And once you're able to achieve all of these equalities, you'd find out that the value for the sums of a squared plus I squared and that of c squared plus g squared is the same thing. And whatever values you get for the sum for a squared plus I squared and that of c squared plus g squared would equally apply to the sums of b squared and h squared and that of d squared, plus f squared. So once you have a uniform sum for the other terms aside e squared, and you're going to equate e squared to n minus, let's say, e squared plus I squared, whatever value you get for e squared in this sense, it's uniform. So that was the idea. So when you come here, um, you find out that down the line, I aborted the idea of going further with this part. I aborted the idea because I realized that if I was going to go further with this formulas for e squared and I squared, what would happen is that, like I said before, when you come here, you might indeed get solutions that satisfy this and satisfy, whatever we saw on the first page as a squared minus I squared equals f squared minus b squared. And that leaves a gap unaccounted for over here. So, which is why down the line we aborted this idea. So when you come here, you'd find out that yeah, so even address that. So you find out that in this case, if you're to stick to that previous formula as we had it, we'll notice a conflicting situation where even though a squared plus I squared equals c squared plus g squared, as required for equation 7, as I showed you, we'll realize a contradiction. And I showed that c squared plus g squared will not be equal to b squared plus h squared, which you can see in this example. That's the sort of gaps that would emerge. So my only way of addressing that, you know, is to, my only way of addressing that was to come to equation 8, going back to equation 8, this one. And when you do a bit of operation work, since we're able to already work out what the formula for b squared and h squared was, it was very easy to just, get c squared plus g squared. It equals to this formula, then some operation work, and then we get this, you know. And when we refer to the page 1 before, we find out that g squared minus c squared is also equal to x squared, so equal to x, sorry, and with a bit of operation work, this is the same as 1, and 1 times x is x. So, we come down here, we do a bit of simultaneous equations over here, and then we get this formula for g squared and this formula for c squared, you know. And ideally, let me read this properly. Yeah. So ideally, once there are known devices for which a 3 by 3 magic square of squares should exist, or at least for which we get integers for g squared and c squared in page 15, what happens is that the resulting equation for c squared is reduced to a problem of two unknowns, being g squared in x or c squared in x. And once this is computed in a calculator tool or computing software like SageMath or Wolfram Alpha, we get values for g squared and x expressed as a function, let's say in terms of t, or you know. So what I'm trying to say over here is the idea is that if you consider this formula we had for g squared, suppose we knew the devices because r subscript 2 and r subscript 4 and also r subscript 3 somewhere, whatever they are supposed to imply that they're devices of x. So if that, so ideally, the goal is that if we know the right values for r subscript 2 and that of r subscript 4, and we made necessary substitutions, whatever formula we would get, whatever resulting equation we'll get, would be in terms of only g squared and x, and if you're able to use computational tools, and we are fortunate enough, that's ideally speaking, we should either get values, value for x and g, which are integer, and by extension, whatever value you get for x in this case, when you put it into the formula for c squared as you have it, c squared as you have it, it should work. You know, that's ideally speaking. Or at least what should ideally happen is that's in order to push the boundary of this problem is that if you have to still go through anyways, whatever resulting formula, resulting equation we get by this thing, suppose we knew the right devices for r subscript 2 and r subscript 4, and were to make due substitutions into this equation or that equation, it was either it was going to lead us to specific integer values for x, which will still satisfy this by the way, and we might only, be able to push this further. That was the idea behind that, you know. But once because these are just preliminary results, we'll stick to our previous example because if you see my previous video, you'd find out that we use example cases of x being equal to 2000, r subscript 4, being equal to 2, that kind of thing. Based on those results we had, we can just test to see whether our formulas function. So these were some results we had. A squared plus I squared equals G squared plus C squared. Based on our previous substitution over here. Yeah. And so what we did over here, that's if I not explained it well enough. What I did here was, or how we got this simultaneous equation is the fact that we went here. You see this gap? You see this gap? We filled this gap. So what we did was that we now make some bit of operation work over here, and we had c squared plus g squared equal to bh plus h squared. And because we already had whatever formulas we had for b squared and h squared, it was very easy to, get c squared plus g squared equals to whatever formulas we had, you know, as one equation, and the other equation coming from the first page, which was g squared minus c squared equals to x. So that was how we did things. And yeah, that was how we were able to get the simultaneous equation, and we worked things out over here. And that was how we were able to get these equations. And so by getting these equations, a squared plus I squared equals to g squared plus c squared, the rest is just operation work, and we got this formula. And then this a squared minus I squared was also previously from, the page 1 of, this work, which was a squared minus I squared equal to, f squared minus b squared, that formula we had. And with a bit of substitution work, be able to get this. And then when you add, because this came from equation 7, I just labeled it equation 7. It's also equation 5. So when you add these two equations, we get this formula. We get this, some cancellation works happens here. And we get this numerator over 8 times r subscript 2 squared and r subscript 4 squared, And so we had these formulas. And so this was our final formula for a squared. And then we came down and got this formula for I squared, So this is the formula we had. And so given these formulas as deduced for g squared, c squared, a squared, and I squared, an example case of 2000 r subscript 2 being equal to 8 and all of these things, we just made substitutions. We just made substitutions to see. So making raw substitutions, we had this 8 different, yeah, eight different, values. And so we find out the only true integers here are b, d, f, and h. The rest are non-integers. This is just by, for the sake of simplicity, we just made raw substitutions, And so after making those substitutions, we find out that all 8 sums are met. All 8 sums are met over here, which is, good. And given the example case we are trying out, we find out that the common sums around the magic square is this. And this means that when you add a squared plus b squared plus c squared, whatever formula you get is the same as a squared plus d squared plus g squared, then c squared plus f squared plus I squared. It's just you get this whatever you do, this is the constant number you get, you know, and then a marker will get the value of e squared, and to get e squared, let's come on top here. To get e squared, let's come on top over here. Let's see. To get e squared, we're just going. There's not too much of explanation we'd even have to do, but just to show something. Oh, let's see. Let's see something. Yeah. And so to be sure what we did was right, to get e squared, what this would mean is that, like I said before, I think I already said it already, but I'll say it again, that a squared plus I squared, whatever this is, should be equal to the sum of this and that. And the value for the sum of this and that should be equal to the sum of this and that and this and that. Already, we already have a constant formula for n, So based on that, once you just have to just take one, you have to just take one equation. For example, e squared equals n minus a plus I n minus a squared minus I squared. And then whatever formula you get for e squared here will definitely apply to the rest. And you have your perfect working magic square of squares. And so when you come down here, um, yeah, that's what we did. So we just made those checks, even based on those simple example cases we had. We just made our own checks to see. So we had this worked, that worked, that worked. And so once we just do this, we're able to determine the example case of e squared to be equal to this, you know. And so given the values and formulas above, it's a goal of the author to increase the number of integer cells from 4 integers to a higher number. But given the nature of the formulas for g squared, c squared, a squared, and I squared, the open question is for which integer values of these divisors r subscript 2, r subscript 3, r subscript 4 do we get integers for g squared and x, you know? So this was the only thing left. So yeah, right. So yeah, so that was the thing. So when you come here, you find out that when you look at this example case in itself, it gives you an idea that in total, out of 9 cells of a typical 3 by 3 magic square of squares, we have 4 integers and 5 non-integers. Um and indeed, I would like to even extend this to push the boundary to see whether we can even hit maybe 6 integers out of 9 integer cells, or maybe 7 out of 9. The goal is to hit that. And we're given the formulas that we have here. I suspect, I mean, if that's an appropriate way to use in mathematics, but that if we tried harder, I'm yet to make those searches myself, but did just a video just to share my latest preliminary result on this problem. That if you're able to use a bit of computational search to search for solutions for this, whatever value we get for x, whatever family of solutions we get for x, and even I squared in this sense, we definitely apply to maybe that of e, because e is kind of similar. So yeah, so if that works, we can even push that to 6 integers out of 9 in a typical magic square of squares, and who knows how far we could even get things. So right now, this is the formula I've been able to get. And so yeah, these are our results for now. I've shared my results on Figshare, which is still handwritten. So over here, where did I see that So I even conjectured something, that whatever value satisfy this, given the question I even posed here, that the open question here is, for what integer values of these values do we get integers for g squared and x, you know? And if we can answer this in the positive, whatever value we get for x, or whatever family of solutions we get for x, would definitely work for the formula involving c squared, and who knows, probably also a squared and I squared. So that's the goal, you know. And so so everything came down to conjecture here that whichever value satisfy this will satisfy the equation for c squared, like I said, a squared, I squared, and probably e squared, but there's a popular opinion that, or the popular, belief that we do not have a full 3 by 3 magic square of squares, you know. And so, yeah, right now I can only push the boundary to see how far we can go with this problem. And so I think this brings us to the end of this video, you know. So I think right now I would only share fix share. Yeah. So this was where I left the results. I updated my results. I updated it so you find out that this is a version 2, and this is a version 2. And so this is, yeah, 23 pages. So this is where we end the video. And so thanks very much for your time. Yeah, and see you next time. Ciao.